Welcome to the Skeptical Chemist YouTube channel, your online lecture hall where chemistry is made easy. In this video, we will derive how the Celsius, Fahrenheit, and Kelvin temperature scales relate to each other, and then use those relations, expressed as equations, to convert between the temperature scales. Temperature is a base quantity in the SI system. This means that it's one of the fundamental quantities from which other quantities and concepts can be derived. Temperature is important and commonly used in science. You will need to know how to convert between temperature scales, but it's also helpful to understand how these scales are related to each other and a little bit about the history behind them. Temperature is a fundamental concept in science, and one key role of temperature is determining the direction that heat flows. For example, if you place a hot piece of metal next to a cold piece of metal, heat will transfer from hot to cold, or down the temperature gradient. This shows that temperature is quantitative. We can observe that heat moves between objects with different temperatures, and we can measure temperature. To obtain a numerical value for temperature, we need both a scale and a method of measurement. So a scale defines reference points and fixed intervals. The most commonly used temperature scales are Fahrenheit, Celsius, and Kelvin. The Fahrenheit scale was invented in 1724 by Daniel Gabriel Fahrenheit. And I mention the year here to put into perspective our understanding of temperature. Humans have long known that some objects feel hot while other objects feel cold. It was only relatively recently, 1724 wasn't that long ago, that scientists developed the ability to quantify this sensation. Now, I do think it's worth going into a little bit of history and logic behind the scales and how and why they were developed. Fahrenheit initially defined the 0 point of his scale to be 0 degrees Fahrenheit, which corresponded to the freezing temperature of a saltwater ice mixture. And then he defined the second reference point as the human body temperature. He used this saltwater ice mixture because it was the coldest temperature he could recreate in lab. And he used the body temperature because it was practical and it was relevant to humans. Later on, he did adjust his scale so that the 0 point corresponded to 32 degrees Fahrenheit, which was the freezing point of pure water, and the upper reference point was 212 degrees Fahrenheit, which was the boiling point of water. So these reference points were more reproducible in other labs, and that's the reason he ultimately changed. In 1742, Anders Celsius introduced a temperature scale with two fixed reference points that were separated by exactly 100 degrees. Celsius also based his scale on the physical properties of water. The 0 point was defined as the freezing point of water, or 0 degrees Celsius, and the second reference point was defined as the boiling point of water, or 100 degrees Celsius. The physical properties of water are universal and therefore easily reproducible. So that's why he chose his scales reference points. Now, in the mid-1800s, William Thomson, later known as Lord Kelvin, introduced a scale that was based on the theoretical foundations of temperature, or specifically on the concept of absolute zero. Absolute zero is the lowest temperature that can be reached. So here, matter has no thermal energy in the classical sense. On his scale, absolute zero is defined as 0 Kelvin, and the size of each degree increment is the same as that of the Celsius scale. That will make more sense when we start working with calculations. It's also worth pointing out that because 0K is the coldest you can get, there are no negatives in the Kelvin scale. And finally, we mentioned that we need an instrument to measure temperature. Generally, we use thermometers. Thermometers are actually really interesting in the way they work. So generally, they contain some substance, such as mercury or alcohol, and that substance responds to temperature changes in a consistent and reproducible way. So when mercury is heated up, its volume increases. This is called thermal expansion. And the amount by which the volume increases for a given change in temperature is determined experimentally. Then mercury is placed in a narrow tube with markings that correspond to a temperature scale. When the mercury expands, the change can be measured, by observing which marking the top of the mercury column reaches. Or let's say you take a thermometer and you place it in contact with some substance, say a boiling pot of water. Heat will flow down the temperature gradient. In our example, because the boiling pot of water has a higher temperature, heat will flow from the water into the mercury until a thermal equilibrium is reached. At this point, the mercury will have expanded in proportion to its temperature increase, and the temperature can be read from the scale. Now let's derive how the Celsius and Fahrenheit scales are related. On the Celsius scale, water freezes at 0 degrees Celsius and boils at 100 degrees Celsius. On the Fahrenheit scale, water freezes at 32 degrees Fahrenheit and boils at 212 degrees Fahrenheit. For temperature conversion, we care about the size of the temperature interval, that is, how many equal increments there are between the freezing and the boiling points, not just the numerical values assigned to those points. And we can get the intervals by taking the difference between the reference points. On the Celsius scale, the change in temperature is 100 minus 0, or 100 degrees Celsius, meaning that the interval between the freezing and boiling points is divided into 100 equal increments. And these increments can be thought of as the degree size. On the Fahrenheit scale, the change in temperature is 212 minus 32, or 180 degrees Fahrenheit, meaning that the interval between the freezing and boiling points is divided into 180 equal increments. Now, if we take the ratio of those two temperature changes, we get delta Tc over delta Tf equals 100 over 180. And we can simplify that fraction by breaking it into factors. And after canceling out the common factors, this reduces to 5 over 9. This means that 1 degree Fahrenheit is only 5/9 of a degree Celsius. Also recall the 0 points between the two scales is off by 32 degrees Fahrenheit. If we start with some temperature in Fahrenheit and wish to convert it to Celsius, we need to make two corrections. First, a scaling factor of 5/9 to account for the different increment sizes of the two scales, and then a shift of 32 degrees to account for the 0-point differences. First, we apply the scaling factor by multiplying the Fahrenheit temperature by 5/9. This converts the temperature intervals between the two scales. Then, since we want to convert to Celsius, which has a 0 point at the freezing point of water, we need to shift the Fahrenheit 0-point value to align with the Celsius scale. We do this by subtracting 32 from the Fahrenheit temperature, since 32 Fahrenheit corresponds to 0 degrees Celsius. This adjustment must also be multiplied by 5/9 to account for the different degree sizes. Notice that both terms are multiplied by 5/9 because both the temperature and the offset need to be converted from the Fahrenheit scale to the Celsius scale. We can simplify this expression by factoring out the common factor of 5/9. And this final equation is the equation to convert degrees Fahrenheit to degrees Celsius. To determine the equation for converting Celsius to Fahrenheit, we can either repeat a similar reasoning process above, or rearrange this equation to solve for Fahrenheit. Let's say we want to rearrange this equation to solve for Fahrenheit. First, let's start with the equation that we have. First thing that we want to do is divide both sides of the equation by 5/9. We can do that by multiplying the reciprocal. When that cancels, we'll be left with the degree Celsius times 9 over 5, which equals to the degree in Fahrenheit subtract 32. And now we can add 32 to both sides of the equation. And so when we do, the negative 32 will cancel with the positive 32. And that will leave us with degrees in Celsius times 9 over 5 plus 32. We can rearrange that and write it with the variable on the left-hand side of the equation, so it's just in a form that is more normal. And this is the equation to convert the temperature in degrees Celsius into Fahrenheit. And now let's derive how the Celsius and the Kelvin scales relate to each other. So remember that both the Kelvin and the Celsius scales have the same scaling factor, or the same temperature increments, and that the 0 point for Kelvin is 0 K. This corresponds to negative 273.15 degrees Celsius. And how do we know those temperatures correspond? From gas laws, we know that as a gas gets cooler, its volume decreases proportionally. And by extrapolating this relationship, the volume of a gas will theoretically reach 0 at negative 273.15 degrees Celsius, which we call absolute zero. Now in reality, gases will solidify or liquefy before reaching absolute zero, so this is based on ideal gas behavior. But to convert from Celsius into Kelvin, we only need to correct for the offset in the 0 point. Remember that on the Celsius scale, absolute zero is negative 273.15 degrees Celsius, and on the Kelvin scale, it's 0 K. So to make the Celsius scale align with the Kelvin scale 0 point, we need to shift the scale up so that negative 273.15 equals 0 K. And we simply just add 273 degrees to do that. So the temperature in Celsius plus 273.15 gives the temperature in Kelvin. And if you wanted to know the equation to convert from Kelvin into Celsius, then you simply solve this equation for Celsius, which is relatively simple. We subtract 273.15 from both sides of the equation, and we can write it neatly, and this will be the equation to convert Kelvin into degrees Celsius. Let's say you're charged with converting 34 degrees Fahrenheit into both Kelvin and Celsius. Now, I know that if I need to get from Fahrenheit to Kelvin, I have to go through Celsius. So let's convert into Celsius to start with. And we'll start with the conversion equation. The degrees Celsius equals 5/9 times the quantity, the temperature in Fahrenheit, minus 32. And now we can substitute 34 degrees in for Fahrenheit, and this gives 5/9 times the quantity, 34 minus 32. Following the order of operations, we can simplify what's inside the parentheses. So 34 minus 32 equals 2. So now we have 5/9 times 2. That equals 10 over 9. And if we convert that into a decimal, we get 1.11 degrees Celsius. Now to convert to Kelvin, we use the formula the temperature in Kelvin equals the temperature in Celsius plus 273.15. And we substitute the Celsius value that we just determined of 1.11, and we add that to 273, so our answer in Kelvin is 274.26. Now let's convert negative 10 degrees Celsius into Kelvin and Fahrenheit. We can convert Celsius directly into Kelvin, so let's go ahead and do that. We can substitute negative 10 into the Celsius place, which gives negative 10 plus 273. So 263.15 is our answer in Kelvin. And now we can convert negative 10 into Fahrenheit. So again, we'll just substitute in the value for Celsius. So negative 10 times 9 over 5 plus 32. So negative 10 times 9 over 5 is negative 18 plus 32. Watch the orders of operations on your temperature conversions. Negative 18 plus 32 is 14. The answer is 14 degrees Fahrenheit. And finally, for our last example, let's convert negative 40 degrees Fahrenheit into Kelvin and Celsius. We'll start out with Fahrenheit into Celsius because we have to convert into Celsius to get to Kelvin anyway. We'll substitute negative 40 into the Fahrenheit. So negative 40 subtract 32, that is negative 72. Negative 72 times 5 over 9 is negative 360 over 9, which simplifies into negative 40. And so this is a fun temperature because negative 40 Fahrenheit is equal to negative 40 in Celsius. And then of course we can convert that to Kelvin by adding negative 40 plus 273 to give 233.15 degrees Kelvin. If you found this helpful, consider giving it a like. It really helps others find this content too. Thanks for watching.